The chapter Laws of Motion is not yet complete. What I have taught you is only the 3 laws and the forces in universe. Today I am going to introduce you to all kinds of forces that we will deal with. In the last session I had described about different forces in nature, and this time it is all the mechanical forces that we are going to deal with in our syllabus, especially in class 11 syllabus, that is mechanics. So let us first start with normal force. This is a very important force you have to remember while drawing all the forces acting on the body. This force is always perpendicular to the surface in contact. So it has to be perpendicular to the surface. Whenever you see that two bodies are in contact, then this force has to be applied. Like if these two bodies are here, so between these two bodies, let this be A and B, A will apply a force on B in this direction, whereas B will apply a force on A in this direction. And according to Newton's third law of motion, these two forces has to be same, equal and opposite, of course acting on two different bodies A and B. So first you have to check what is the surface that is in contact, and then you have to draw a force which is perpendicular to the contact. Now for drawing this force, you have to remember that if a body is applying the force on another body, it has to be in a direction so as to push the other body. Like if A is applying force on B, then A will push B apart. So it has to be force on B due to A. This is force on A due to B. A is pushing B and B is pushing A. So this force is actually pushing in nature. It pushes the other body away. This is how normal forces is applied whenever two things are in contact. One more thing is there, it has no definite value. This is a self-adjusting force. According to the situation, this value will keep on changing. If we take a circular track like this, and let some vehicle is moving against this track. So when it is at the lowermost position, what will be the direction of normal that is applied on the vehicle from the track? It has to be in upward direction. So this is N. Of course, weight will act downward, and since it is moving in a circular orbit, so towards the center there has to be a centripetal force. So from here we can write N minus mg should be equal to mv square by r, because towards the center one effective centripetal force has to be there, and this force will be provided by the force N minus mg, which is resultant force in upward direction. So from here we can write N is equal to mg plus mv square by r. Now what happens when this vehicle comes to this topmost position? This time again circular track will push it away, so normal will be in this direction and mg also is in this direction. Now if it continues moving with the same speed, then we have to write N plus mg, because here both are acting in same direction, that is towards the center. So this both will provide centripetal force required, and from here N will be equal to mv square by r minus mg. So you can see according to the situation, value of N will change. That is why it is called a self-adjustable force. So this is the force we have to apply every time whenever two surfaces are in contact, whether it is a horizontal surface or vertical surface or some inclined surface. Every time this has to be applied. So do remember applying normal force whenever two contacts are there while solving a numerical. Let's now move to next kind of force that we will encounter with in our mechanical system. This is tension. Now tension is a force which is applied in a string. If it is a taut string or a wire, in this kind of thing tension is applied. And what kind of force is this tension? It is always pulling in nature. So few characteristics are there for tension force. First thing is that it is always pulling in nature. Never it can push a thing away. So it has to be pulling. Always it pulls towards itself. So this is pulling in nature. The second thing is that its value is self-adjustable. Again, according to the situation, its value will change. So this is called self-adjusting force. We can take one example. If with the help of a string, one bob is hanging here and this point is fixed, if it is rotated in a vertical circle, while in the lowermost position we have to write tension is in upward direction, mg being in downward direction, we have to write T minus mg is equal to mv square by r. And if it continues to circulate with same velocity, then at the uppermost point you can see, as in previous case, tension and mg both will be in the same direction. So this is mg and tension both, and the combined force have to applied the centripetal force required. So in these two conditions value of T has changed. If at this position it is written T, so at uppermost position it will be having somewhat different value. That is why it is called self-adjusting, because according to the need its value adjusts itself. The third thing is, that is specific of tension, that if we consider a massless rope, which is the general case for a numerical problem. Of course you can get a numerical when mass of rope will be given, but generally if it is an ideal rope, massless rope is given there, then you have to write tension has to be constant throughout the length of rope till rope is continuous. If it is broken at some point or tied to some other thing, then of course tension will change. Otherwise its value will remain the same throughout the length if it is considered as a massless rope. But of course here continuity has to be checked, because if some other thing is tied, like if this is mass 1 and with the help of rope the other object is tied here, which is another mass m dash, and in between if it is an ideal rope, then from this block to this block value of tension will remain the same. But if in the middle we tie it to another block, let that be m double dash, then of course tension on this side and tension on this side will be changed, will be different. It will be constant if the rope is continuous. The next force that we will encounter is spring force. If we consider a system in which spring is attached, then a spring force has to be applied on the body to which it is connected, and that is given by Kx, where this K is called spring constant and this X is called extension in the spring. It is not only extension, it can be even compression. So whatever it be change in dimension, that has to be considered here. So this is extension or compression. And in what direction does this force act? It has to be opposite to X. So one minus sign has to be put here. If it is extended, it will try to come in its natural length, and if it is compressed, again it will try to come to its natural length. So whatever be direction of X, force has to be opposite to that direction. This is the nature of spring force. As you can see, it linearly depends on X. So its value will not be constant throughout the extension. This value will remain changing. We will see some examples in which spring force will be applied and then check how numericals be solved. The next force that we have to write every time is which is weight. Now as you all know, you are very familiar to this force. It is the force which is exerted by earth and its value is given by mg. Only one mistake generally students make, they think that direction of this force is vertical, whereas it is not vertical, it is towards the center of earth. So its direction is towards center of earth, not vertical but about center of earth. Actually vertical direction is a relative term. If you are standing here on the earth, then this is vertical direction for you. If someone is standing here, then for that person, this will be the direction of vertical. If someone is standing here, for that person, this will be the direction of vertical. If someone is here, this will be the direction of vertical. So vertical is not a constant direction. It is related to from where you are observing, from where you are standing. So vertical direction cannot be said as direction of weight. It has to be towards the center of earth. Wherever you are, this force will pull you towards the center of earth. So this is how weight is written. Its value will remain constant as far as g is constant, which generally will be throughout the chapter. Only this value will change with greater heights or greater depth that we will deal in the chapter gravitation. So here its value will remain constant, that is equal to mg. Next force is force of friction. Now this is very important and we have to see whenever the surfaces in contact are rough, then only this force is applicable. So when surfaces are rough, then we have to apply, along with all other forces, we have to apply friction also. But in what direction? It has to be opposite to the direction of relative motion or tendency of relative motion. So it has to be opposite to relative motion or its tendency. This is the direction of friction. What about its magnitude? Later we will discuss in the coming session about friction in detail. For now we can exclude the questions where this friction force is involved, because it is a very large portion, we have to deal it separately. Now after discussing all the kinds of forces in mechanical system that we have to consider while solving a numerical problem, let us first see what is called this free body diagram. You must have heard this term free body diagram. It's very popular among students. So what is this free body diagram? See, while solving a physical situation involving a lot of bodies in contact, directly writing equation for the whole system is generally not possible, because it would be very complicated mathematically. So what we do, we separate all the bodies that is inside the system and draw free body diagram for each body, then write the equation for that particular body. In this way we can easily solve a given situation. So let us see, if this is the situation given here, let this be mass of the block here m1 given, this is m2, and I am considering that this wedge is fixed, angles being theta 1 and theta 2, we have to draw free body diagram for m1 and m2. So how is it drawn? First isolate the body from the whole system. So I have isolated body m1 from the whole system. Then you have to, first step is to isolate the body. In next step we have to write all the forces that is applied on the body. So we have to show all the forces that are applied on the body. Do remember, because while drawing free body diagram, generally students also involve the forces that the body is applying on other bodies. No, this is not to be done. Only we have to draw the forces that are applied on that particular body. So if we consider this particular body here, which is m1, what forces will be applied on this? It has to be one weight mg, and then normal has to be always perpendicular to the surface in contact. So let us draw this. Can you see any other contact? Of course, it is with this rope. So rope will apply a tension, always it has to be pulling, so that rope is pulling it towards itself. So these are the forces applied on the body m1. We are not drawing the forces which m1 is applying on the wedge or it is applying on the rope. Only we have to draw the forces which are applied on the m1. So this is the way in which free body diagram is drawn. What about the wedge? If we are interested in drawing free body diagram for the wedge, then it will be having the forces. Now its weight has to be there. Let mass be capital M. Then it has to be mg. Of course, from the ground, one normal reaction has to be there. Let that be n dash. Now from here, because it was applying a normal force n to m1. So in opposite direction, that normal force will be applied by block m1, which is n. This is also in contact with m2. So m2 will also apply a force. Let that be n2. Is there any other force? Of course, because pulley is attached directly to the wedge. So whatever be forces applied on the pulley, it has to be the same forces on wedge also. Now what forces are applied on pulley? As you can see, it is shown by red arrows. Thus the two parts of strings are pulling it in the shown direction. So that will be the direction for wedge also. So in this direction, let the tension be T. So in this direction one tension, and again in this direction one more tension having the same magnitude. So these are the forces applied on the wedge. In this way we have to draw free body diagram and show all the forces acting on the body. Now I am coming to the very important part, because generally what happens when students read a concept written in book or learn it from somewhere, from some teacher or from some video lesson, then he is able to understand the concept. This is true for almost all students. They are able to get the concept, though not able to solve the numericals. So to solve a numerical, first we should know how the concepts that we have learned will be applied to the given situation. That is the most important thing for preparation. Now I am going to explain you what should be the strategies to solve a given numerical. First, what we have to do for the given situation, First we should draw free body diagram. This is the first step we have to follow. So free body diagram has to be drawn first. First step is free body diagram. Then all the forces to be shown. After that, the very important step has come when we have to write the equation. Now you generally get this confusion that in which direction it should be written, whether along horizontal or vertical or in any other particular direction. For this you have to remember, if the given body for which you have drawn free body diagram, if it is having acceleration in some direction, then you have to write F is equal to ma in that particular direction. So we have to write F is equal to ma in direction of acceleration. Understood this clearly? In which direction we have to write F is equal to ma? In the direction of acceleration of body. Now here sometimes it would be more convenient if this can be written in component form. Like if it is along the incline, then we may take, let us consider one situation in which there is a wedge on which a block is placed here. Of course, with respect to wedge, the block will be having this much acceleration, let that be a1, and if this wedge also is moving, let this be the direction of acceleration for a2. Then in which direction we will write the equation for block M or for wedge? For here we have two choices. Either we can consider horizontal as x-axis and vertical as y-axis, and then write all F is equal to ma in vertical or horizontal direction. Or other option is that we can take along the incline as x direction and perpendicular to incline as y direction, and then write all the equations accordingly. So here we have two choices because both a1 and a2 are not in a single direction. So according to the convenience, we have to write F is equal to ma in any particular direction. If there is only one body moving, then F is equal to ma directly can be written in direction of acceleration of that particular body. So the third step is we have to write F is equal to ma in direction of acceleration. Either it can be directly written in that direction or its components can be written in two other rectilinear directions. The next step is, if it is in equilibrium, if the given body is in equilibrium, then we have to write net force on that to be 0. Now here a number of forces can be applied on the body and still the body may be in equilibrium. Then you have to write vector sum of all the forces to be 0. It is not always possible that all the forces will be in the same direction. It can have any direction. So you have to write vector sum of all the forces to be equal to 0. Here one more very interesting thing is there, that if vector sum of a force is 0 and you know that F can be written as Fxi plus Fyj plus Fzk. So magnitude of F can be written as square root of Fx square plus Fy square plus Fz square. If this is 0, then of course individually Fx, Fy and Fz all have to be 0, because as we can see all are square terms, so these cannot be negative. So if F is 0, individually we can write Fx, Fy and Fz all to be equal to 0. This will help you in solving the question very much, because always writing the vector sum is a little complicated. So it is always better to write the equation in component form. If body is in equilibrium, we can write Fx is equal to Fy is equal to Fz to be 0. So this is the fourth thing we have to keep in mind. One more very important thing is there, that if body is not in equilibrium, already we have written F is equal to ma in direction of acceleration, but still one variable is there which we are not able to solve. Then we will need one extra equation. How can we write the equation? Then we have to write F is equal to 0 in direction perpendicular to acceleration. This is very important one. Generally students do skip this step, because if number of variables are more and you have already written F is equal to ma, still you are not getting the required number of equations. So you have to write F is equal to 0 in direction that is perpendicular to acceleration, because if acceleration is in certain direction, then its rectangular component has to be equal to 0. These are the steps to be followed while solving a given numerical. Let us consider one example more. In the given question, a uniform rope of length L and mass m is placed on a smooth fixed wedge as shown. Both ends of rope are at same horizontal level. The rope is initially released from rest. Then the magnitude of initial acceleration of rope is. To explain this, let us first write the lengths of rope on both the side of wedge as L1 and L2. Then if we write force equation for the part L1, what forces are acting on this? One normal reaction has to be there. Another will be its mass, let that be m1. So m1 into g, which is the weight, and one tension will be here in this direction along the incline, where the incline is having angle alpha with horizontal. Now if we write equation of motion for this part of rope in the direction that is along the incline, it will be having expression m1g sine alpha minus t to be equal to m1a, where we are considering that the left part is coming down with acceleration a along the incline. And what about the second part? For second part, again let us draw FBD. Here normal will be having some different value, let that be n2. Tension at the uppermost point will be having the same value, that is T, and then weight, which is m2g. For this, now we have to write acceleration in direction that is along the incline but in upward direction. Here angle of inclination is given beta. So if we write equation for this part, it will be T minus m2g sine beta to be equal to m2a. Now let us add these two equations. The term t will be cancelled and finally we are going to get m1 sine alpha minus m2 sine beta, this whole multiplied with g, to be equal to, this is m1 plus m2, so that will be equal to mass of the whole rope, which is given here m. So m times a. And now the acceleration comes out to be, a is, we can write m1 and m2 as, if linear mass density, we can write that will be m by L. So if m by L is taken outside, that is the linear mass density, for part m1 we will be having the length L1 sine alpha minus, for second part the length is L2, so L2 sine beta, and this whole divided by capital M. This is the expression for acceleration. But from geometry, as initially the rope is at rest, it has been released from rest. So from geometry we can say that L1 sine alpha should be equal to L2 sine beta. And on substituting this value, we will get A to be equal to 0, which is our correct option, that is option number A. Okay, massive rope system. Now what I had said while explaining the force tension, that tension has to be continuous throughout the length of rope. If rope is assumed ideal, it is assumed massless and no other object is tied in between. Then we can write tension as constant throughout the length of rope. But what if the given rope is having mass? So then we cannot consider tension to be equal at all the points. We have to write the equation for each part of rope. Let's draw the situation. This is the rope having length L and it is pulled with help of force F at one of its end. If we have to write tension at this intersection, which is at a distance x from this rope. So let us now consider this part as independent. I am drawing FBD for this right half part. What the forces are there? On right hand side it is F, and on left hand side let this be T, where T is the tension at a distance x from the given end, which is the right end where force is applied. So this distance is x. What will be the value of T? Now if the whole rope is moving with some acceleration A, of course this part also will be moving with the same acceleration A. So for this part we have to write F is equal to ma. What the resultant force is there? That is F minus T has to be equal to mass into acceleration. Now we have to write mass for this x part only. What it would be? If mass for the whole rope is m, then it has to be m by L into x. This is mass of the shown part. This multiplied with A. Now let us first calculate value of A. It can be written as F is equal to, for the whole string if I write, that will be equal to F is equal to MA. From here we can write A is equal to F upon M. If we substitute this value here, it will be reduced to, in place of A I can write F by M. This M got cancelled. So we got F x upon L. What is the value of T then? T can be written as F minus Fx upon L. If F is taken common, this is 1 minus x by L. So this is the tension at a distance x from the end where the force F is applied. Here you can see that tension is dependent on x. It is not having a constant value. As x will change, this tension will keep on changing. So this much we discussed in the current session, and we will do some more questions. We'll see some more examples in coming session. Till then, goodbye.